All right, for the purposes of this module, what we're going to be talking about is energy. Uh, Now, the interesting thing about energy is it's entered the English lexicon fairly easily, but not a lot of people talk about what it actually is. So the idea behind energy is a little more complicated than it's made out to be. Typically speaking, when people refer to energy, they refer to it as if it's a physical thing, something you can have, right? So if you're tired one day, you say, "Man, I don't have any energy today," right? You know, if your computer dies, you say, "Well, it ran out of energy." Now, the problem with that is if I have a box uh, and I try to, say, fill it with energy, right? So let's say you want to take energy and you want to put it in a box. How do you actually go about doing that? Like, the trouble is I can't take a bucket or a box and put energy into it. I can put gasoline into it. I can put food into it. I can, start a fire inside it. I can do all of those things, but energy by itself, like, I can't put it in there because the question becomes, well, what do I put in there? What physical object do I put in there? And this is actually resolved by understanding what energy actually is. The main takeaway here, at least conceptually, is energy is not physical. In other words, it's not a thing that you can hold in your hand. It's not a thing that you can, grab onto, possess, demonstrate, show to me, or anything like that. So the question is, if it's not a physical thing, why do we use it? Well, at the end of the day, energy came about for a very specific reason. Up until now, you've been solving problems with forces and torques and that kind of thing. Those are all vector quantities, and one of the difficulties with dealing with forces and torques, or Newtonian style mechanics, is it doesn't scale up very well. What you may have noticed is the problems can get very difficult very, very quickly. Now, energy was introduced by primarily two European mathematicians, Hamilton and Lagrange, and Hamilton is not the guy that the current play is based off of. It's a British Hamilton. To simplify Newtonian mechanics, they introduced energy as a quantity that is conserved. In other words, it does not change if you have nothing external acting on your system. So in other words, it's, I spelled that terribly wrong, conserved in isolated systems. So what this means is energy, realistically speaking, is a math construct or an abstract idea. It's not a physical thing that you can actually have. But we use it like that, or we think about it like that sometimes because it's incredibly useful due to this fact that it is conserved. In systems, it's transferred, technically speaking, between one form and another. And the main reason why it's so useful is because at the end of the day, it's a scalar. It is not a vector. It has no direction, and you only need to keep track of how much you have. Now, energy can come in various types, such as kinetic energy associated with moving objects, chemical energy associated with chemical bonds. You can get energies by opposing a force, such as gravity, all sorts of different things. But the idea is, because it is conserved, it's very, very easy when solving problems to transfer it between one form and another. And what you'll find is it makes solving problems about like a ludicrous amount easier than it normally would be. Because you don't really have to keep track of the time dimension or how quickly something's going. You don't really need to keep track of different directions. All you have to do is keep track of how much you have. In other words, instead of having to be a proper mathematician or a, you know, more quantitative scientist, you can actually just be an accountant. You can literally just sit down and keep track of how much you have. And that's what we're going to be doing for this particular section. Uh, so if you're reading the notes, you'll notice that there's a bunch of different types of energy here. We'll even be introducing more types as the course goes on. But the nice thing about this is the problem solving process for dealing with energies is exactly the same every single time. Doesn't matter what types you have, you can process every single one of these problems in the exact same fashion. And that's what we'll be working on in the example in this section. This process that I'm going to show you is relatively successful for students, never really changes, and it basically solves all the problems that you'll be presented with in terms of energy. Now, the very last thing I will mention is the units of this conserved quantity or energy. The units that you will find for energies in the SI system are joules. And a joule is simply equal to a kilogram multiplied by a meter squared per a second squared. So typically speaking, when dealing with energy, you'll see it in joules. Uh, since we're in the United States, you may see energy written in calories and other forms. The calorie is my least favorite unit of energy because calories and calories are different, which is my main personal gripe about them. And if you've done any nutrition, this should have been brought up at some point in time. But we're going to be using joules almost explicitly.